This Bangalore Science Farm started in 1962. I was saying that I was a student and Professor H.R Krishna was a student. And in 67, H.R Krishna Murthy was a student. At that time, Bangalore Science Farm is somewhere in a room, ordinary room. The cinema used to bring some 5-6 people like that. And there used to be some science lecture. Actually, we used to invite a very good persons, even like Verma and other things. But still we had an audience about 10-15 like that. And people used to make fun of me, generally. I am a chair of Dr. H.S. in the sense, every science lecture I used to go. And people also felt that this can't go forever, It will be for 2 years, 3 years, afterwards they will wind up or something like that. Because the audience was not there. Such a room was not there. And such a publicity was not there. But just imagine now, after 56, 57 years, where the scientists in lecture in a multimedia hall, and 200 economic science, and 200 audience for a subject like physics. If it was something like IT or something like that, a different issue. And such a lecture, that to numbering 2,770, mind-boggling number, 2,770 lecture. And with the minutes shortly going to be delivered by Dr. H.R Krishna Murthy, Professor, Department of Physics, University of Science, on the fascinating world of ultra-cold trapped atoms. Today, on behalf of the institutions, and on behalf of you, and on behalf of me, I extend a very cordial welcome to Dr. H.R Krishna Murthy. Of course, after his initial schooling at the National High School, then he got the first time in the National High School, and then joined PUC, and then went to honors courses in Central College, where he got again the first rank, always first rank student. First rank is no more than. Of course, now I can recall one person, I don't know whether he knows it or not. Dr. R Krishna Murthy, Purdue University, EC department, almost founder, chairman, and ಅವರು ನಾವು ಹೇಳ್ತಾರೆ 1957-58. For the first time, a student of the National College got first rank. Try to break this record. Until then, he never got rank or first rank like that. No? First time, he got the first rank for the National College Assembly in intermediate class. No? Of course, later on, first time he went to state, he did Harvard. The physics PhD, then went to EC department of Purdue University, built up that university, and so on and so forth. Other things are history, So like that, our own student, then MSc IIT Kanpur. IIT Kanpur means again CNR Association. He has given Professor CNR here more than 30 lectures, not 1 or 2 lectures, okay? And this multimedia hall was inaugurated by CNR and the governor, and incidentally, 1 hour video conference with the Purdue University. This all. Then MS from Cornell University. Cornell is a very top university. Of course, the first time, I know several people, but Anurag Kumar, if I am correct, the first person who was introduced to me long back from Cornell University, and then PhD from Cornell University. Cornell is a very well-known university, 74-78. Thesis topic: renormalization group approach to the Anderson model of dilute magnet alloys. Don't worry about that. But next one is more fascinating and more important. His thesis advisor is Professor Kenneth G. Wilson, a Nobel laureate. Just important person. Dr. Balaram he had worked with, and I think the person name was Woodward, the Nobel laureate and postdoctoral, on the electromagnetic, if I am correct. Then institute contacts that. They would not have done these things, Over Nobel laureate the Nobel laureate process actually. Nothing else, It's so difficult. But the ambition of any scientist, to work with the Nobel laureate. Things how to chemistry, how to mathematics, how better. And research interest, theoretical condensed matter physics, with a focus on strongly interacting quantum and classical many-body system, especially quantum impurity physics and theories of strong correlation phenomena in solids. Of course, Monday condensed matter and space physics seminar. Because E.S. Kiran Kumar is so well known to us, that was possible. Then, he has a position strength in Samana of Shvetsa, but in the head of particular youngsters. research associates at University of Illinois, Australia, Urbana is important, Illinois, or standard of the USA. Then Department of Physics is working as a industrial science. Then Nordita, Copenhagen, Denmark. Then Physics Department, Ohio State University, Columbus, Ohio. Namge, Ohio, Bharat, Samada. ತಮಾಷೆ ಹೇಳಿದ್ರೆ ಇವತ್ತು ನಾನು ಉಪ್ಪಿಟ್ಟು ಮಾಡಿಸಿಲ್ಲ ಅವ್ರಿಗೆ. ಉಪ್ಪಿಟ್ಟೆ ಬಹಳ ಫೇಮಸ್. ಯಾಕಂದ್ರೆ ಹೆಚ್ಚಿನವರು ಸ್ಟ್ರಿಕ್ಟ್ ವೆಜಿಟೇರಿಯನ್ ಎಲ್ಲೂ ಇದು ಮಾಡ್ತಾ ಇರಲಿಲ್ಲ. ಆಲ್ ದಿ 2.5 years ಅವರೇ ಮಾಡಿ ಉಪ್ಪಿಟ್ಟು ಎರಡು ಜನ ಕೊಡ್ತಾರೆ. ನಾನು ಹೇಳಿದ್ರೆ ಬೇರೆ ಗೊತ್ತಾಗಲ್ಲ. ಇನ್ ದಟ್ ವೇ Ohio State, not only several reasons that Ohio State other time on that. Then comes to our Einstein's Prize, Physics Department, Princeton University, Princeton, New Jersey. Something remarkable actually. And Ohio State University. And then reaches forward, visiting professor, Physics Department, Harvard University. At Cambridge, Massachusetts. Then Physics Department, University of Cincinnati, Ohio. Then Physics Department, University of California, Davis campus. Stress ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಮುಂದೆ ಬರ್ತೀನಿ ಆಫೀಸ್ ಯಾರು. Physics Department, Georgetown University, Washington DC, USA. Then Physics Department, again University of California, with Davis campus at Santa Cruz, second campus. Then again Department of University of California, Riverside. And then Physics Department again at Georgetown University. Then I have number students district professor. Then Department of Physics at Institute for Quantum Information Matter, California Institute of Technology, Pasadena. All campus topics. Really great. California one campus was not there, but totally. In fact, science from here. The order of the day is information technology. Has information technology totally. But a person with pure physics background, speaking math basically new chemistry stories actually. The chemistry because they advent or the IT against IT physics is the whole camera. Actually. Even put Yuri Miller ವಿಚಾರ ಗೂಗಲ್ ಮಾಡಬೇಕು ಅದು ಗೂಗಲ್ ಮಾಡಿದ್ರೆ ಎಲ್ಲ ಹೇಳಿದ್ದೀರಾ ಸಾಧ್ಯ ಹೇಳ್ತೀರಾ. ಇಫ್ ಯು ವಾಂಟ್ ಎನಿ ಮನಿ ಫಾರ್ ಫಿಸಿಕ್ಸ್ ಗೋ ಅಂಡ್ ಆಫ್ ದ ಡಿಲಿಂಗ್ ಇಂದ ಅಷ್ಟು ಓಪನ್ ಇದ್ ಕೊಡ್ತಾರೆ. ಸಂಡೇ ನಾವು ಮ್ಯಾಥ್ಸ್ ಎಲ್ಲ ಗೌರ್ಮೆಂಟ್ ವಿದ್ಯಾರ್ಥಿ ಆಗ್ತಲ್ಲ ಈಸ್ ರೆಡಿ ಟು ಗಿವ್ ಇಟ್ ವಾಟ್ ಎವರ್ ಇಸ್ ಲರ್ನ್ ಥ್ರೂ ಗೂಗಲ್ ಅಂಡ್ ಅದರ್ ಥಿಂಗ್ಸ್ ಈಸ್ ರೆಡಿ ಟು ಗಿವ್ ಇಟ್ ಫಿಸಿಕ್ಸ್ ಸಬ್ಜೆಕ್ಟ್ ಆ ರೀತಿ ಇದೆ. ಬಟ್ ಸ್ಪೀಕರ್ ಕಡೆ ಕಷ್ಟ ಸಡನ್ ಆಗಿ ನಾವು ಆಕ್ಚುಲಾಗಿ ಕೇಳಿದೆ ಅವರು ಕೂಡ ಬಿಸಿ ಆಗಿರೋ. ಬಟ್ ನಾನು ವಿಚಾರ ಗೊತ್ತಾ ಬಿಡ್ಲೇ and I agreed for that. Because ನಾನು ತುಂಬಾ ಸಂತೋಷ ಆಗಿದೆ. ಅಸಬ್ಜೆಕ್ಟ್ ಆಗಿದೆ ಟೋಟಲ್ ಆಗಿ. ಇಂಥ ವ್ಯಕ್ತಿಗಳು ಸಿಗೋದು ತುಂಬಾ ಕಷ್ಟ ಆಗುತ್ತೆ. ಐ ಥಿಂಕ್ ಜಸ್ಟ್ ಲೈಕ್ CNR, ಬಲರಾಮ್, ಪದ್ಮನಾಭನ್ ನಾನು ಆಸೆ ತೋರಿಸ್ತಾ ಇದ್ದೀನಿ. ಇವರು ಎವ್ರಿ ಇಯರ್ ಬಂದು ಮಾತಾಡೋದು ತುಂಬಾ ಕಷ್ಟ ಆಗ್ತಾ ಇದೆ. ಬಲರಾಮ್ ಮತ್ತು ಮ್ಯಾನ್ ವೆರಿ ಫ್ಯೂ ವರ್ಡ್ಸ್. ನಾವು ಫೋನ್ ಮಾಡಿ ಕೇಳ್ತೀರಲ್ಲ ನಮ್ಗೆ ಮಾತಾಡಕ್ಕಿಲ್ಲ. ಎಸ್ ಅಷ್ಟೇ ನಮಗೂ ಇಲ್ಲವೇ ಇಲ್ಲ. He doesn't have any dictionary, no, absolutely. So, ಆ ಟೈಪಲ್ಲಿ ಅವರು ಹೆಚ್ಚಾಗಿ ಮಾತಾಡೋದು ಆಕ್ಚುಲಾಗಿ ಹೇಳಿದ ತಕ್ಷಣ ಮಾಡ್ತಾರೆ ನಮಸ್ಕೊಂಡು ಬಂದ್ರೆ ಐ ಥಿಂಕ್ ಯು ಕ್ಯಾನ್ ಟೇಕ್ ಸೈನ್ಸ್ ಫಾರ್ಮ್ ಈಗ ಫಿಸಿಕ್ಸ್ ಗೊತ್ತು ತುಂಬಾ ಕಷ್ಟ ಆಕ್ಚುಲಿ. ದಟ್ಸ್ ಮೈ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಟೋಟಲಿ. ಅಂಡ್ ನೌ ದಿ ನೆಕ್ಸ್ಟ್ ಒನ್ ಈಸ್ ಟುಮಾರೋ ಎಸ್.ಎನ್. ಓಂಕಾರ್ ಅವರು ಫೇಮಸ್ ಗೊತ್ತಿರ್ತಾರೆ. ಇಂಡಿಯನ್ ಸೈನ್ಸ್ ತೋರಿದೆ ಚೀಫ್ ಫಿಸಿಕ್ಸ್ ಸೈಂಟಿಸ್ಟ್ ಅಟ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಆಫ್ ಏರೋಸ್ಪೇಸ್ ಇಂಜಿನಿಯರಿಂಗ್. ಅಷ್ಟೆಲ್ಲ ಕೆಲವು ಗೊತ್ತಾಗುತ್ತೆ. ಬಟ್ ಇವಾಗ ಹೇಳ್ತೀವಿ ಅನಿಲ್ ಕುಂಬ್ಳೆಗೆ ಪರ್ಸನಲ್ ಫಿಸಿಯೋಥೆರಪಿಸ್ಟ್. ಅನಿಲ್ ಕುಂಬ್ಳೆ ಹೆಸರು ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಅನಿಲ್ ಕುಂಬ್ಳೆ ಹೇಳ್ಬಿಟ್ಟು and they're going to speak on uninhabited aerial vehicles. Yes, interesting. Uninhabited aerial vehicles for all the inhabitants. What a beautiful subject. What a latest subject actually. Omkar is story. Don't worry. Dr. Krishna Murthy, coming from National Center for Biological Sciences, will speak on butterfly stories from biology to conservation. Then an expert in it. Naraji, our student again at University of Science and Professor, Chairman Electrical Sciences, will speak on blockchains. That is the latest technology. ನಾವಿದ್ರೂ ಸೋಷಿಯಲ್ ಮೀಡಿಯಾ ಅನ್ಕೊಂಡಿದ್ವು, ಬಿಗ್ ಡೇಟಾ ಅನಾಲಿಟಿಕ್ಸ್ ಅನ್ಕೊಂಡಿದ್ವು, ರೊಮ್ಯಾಟಿಕ್ಸ್ ಅನ್ಕೊಂಡಿದ್ವು, ಆರ್ಟಿಫಿಷಿಯಲ್ ಇಂಟೆಲಿಜೆನ್ಸ್ ಅನ್ಕೊಂಡಿದ್ವು. ಅವೆಲ್ಲವೂ ಮುಳುಗಿಸಿದ್ರು ಬ್ಲಾಕ್ ಚೈನ್. ಹಾಗೆ ಮುಗಿಸುತ್ತೆ ನನಗೆ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಟೆಕ್ನಾಲಜಿ ಫಾರ್ ದಿ ಫ್ಯೂಚರ್ ಡಿಜಿಟಲ್ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ಸ್ಪೀಕ್ ಇನ್ ದಿಸ್ ಪ್ಲಾಟ್ಫಾರ್ಮ್. ನಾನು ಅವ್ರು ಕೇಳಿದಾಗ ಎಷ್ಟು ಸಂತೋಷ ಪಟ್ಟು ಅಂತ ಹೇಳಿದೆ, ಸರ್ 6 months ಇದೇ ಕೆಲಸ ಮಾಡ್ತಾರೆ ಬ್ಲಾಕ್ ಚೈನ್ಸ್ ಮೇಲೆ, ಐ ಆಮ್ ರೆಡಿ ಟು ಕಮ್ ಅಂಡ್ ಟಾಕ್ ಟು. ಬ್ಲಾಕ್ ಚೈನ್ ಯಾರು ಅರ್ಥ ಆಗ್ತಾ ಇಲ್ಲ, ಎಕ್ಸೆಪ್ಟ್ ನನಗೆ ಹಿಂದೂ ಪೇಪರ್ ನೋಡಿ ಫ್ರಂಟ್ ಪೇಜ್ ಹಿಂದೂನಲ್ಲಿ 5 ಲಕ್ಷ ರೂಪಾಯಿ ಕೊಟ್ಟು ಒಬ್ಬ ಅಡ್ವೈಸ್ ಮಾಡಿದರೆ ಇನ್ನು ಬುಕ್ಸ್ ಕಡೆ ಬಂದು ತಗೊಳ್ಳಿಲ್ಲ. ಅದು ಎಷ್ಟು ಇಂಪಾರ್ಟೆಂಟ್ ಬ್ಲಾಕ್ ಚೈನ್. Currently attend all these lectures, not only yourself, your friends also. With this again, I welcome Dr. Krishna Murthy to present the lecture.
Do I need a mic or
Yes,
audible?
No, make better.
Okay.
Yeah, you make better.
Yeah, so thank you, Dr. Ramana, for the very kind introduction. It's a very great pleasure to be here in my alma mater, and Professor H. Narasimhaya is one of my heroes. I mean, he took a very great interest in my career, and we were in touch even after because he was also my teacher during my pre-university, and he kept in touch with me and took a lot of interest in my career. So it's a privilege to be here, and also many of my friends and classmates. Thank you for coming. So, all right. I thought I will. This is a slightly technical subject, but I thought I will talk about this particular aspect of it, called ultra-cold trapped atoms. Some of you may have heard about it here and there. It's a field which is very active now, and it's come up in the last 15-20 years in a major way. And in particular, in this field and slightly related subjects have won Nobel Prizes, already 4 of them, from 1907, 2001, 2009, 2012. So it's really like a hot subject, and it will be much more in the news in the future as well. Okay, so this talk I have put together with actually I should acknowledge web pages and presentations of many cold atom physics colleagues whom I have happily lifted slides from. Okay. Alright, so here is a rough plan of my talk. I'll tell you a little bit about the background and motivation for why these systems are interesting, why did people work on these kinds of systems, and tell you a little bit about cooling and trapping of atoms, Bose-Einstein condensation. These won Nobel Prizes already, and then some more stuff. I don't know whether I'll get to all of it, but so the idea is not to make you understand everything, but I hope I'll at least titillate your interest in the subject so that you can go and read about it. There are enormous amount of material available about the subject on the web and YouTube. There are other people who are practitioners in this field, given lectures, everything is available. So I hope I'll succeed in that. Alright. So, as you know, most of the matter on Earth is made of atoms. And so this idea that matter is made of atoms is one of the most important foundations of modern science actually. So if you start from something like a flea, which is about 3 millimeters in size, and if you were to magnify it, then it consists of cells, and then if you magnify it further by another factor of 1000, it consists of protein and so on. And if you really go magnify it by a huge amount, you go to the scale of a nanometer, like 10 to the power of minus 1 part in a billion meter, then you come to an atom. So, it's basically, we are making models of it. We can't see it, so we are picturing it in various ways. And depending on the context, we picture it in different ways. An atom consists of light, negatively charged electron moving around heavy, positively charged nuclei. And I'm going to say a little more about this, but let me summarize what's the bottom line. Under the influence of electromagnetic forces and obeying, this is very crucial, obeying the laws of quantum mechanics. The laws at the scale of the atom are completely different from Newton's laws and other things that we are used to. So without appreciating quantum mechanics, it's very hard to understand what's going on in the atomic world. So there are some important aspects of this. So what are the basic features of quantum mechanics? One is something called the dual nature of energy carrying entities. What we think of normally as particles, we think of energy carrying entities as particles or energy carrying entities as waves, and these are two disparate kinds of objects in normal experience. But in the quantum world, every energy carrying entity has both characteristics, and I'll say a little more about what this is. And there is this principle of superposition or interference of probability amplitudes of different alternatives, something called the Pauli principle, that I'll say a little more about, and something called the Schrodinger equation. And these are the basic essential aspects of quantum mechanics, and these determine the motion of electrons around nuclei. And amazingly, this leads to everything that, all the properties of matter, basically the stability, shell structure, spectra, other properties of atom, periodic table, chemical bonds, structure and properties of molecules, matter around us in all the myriad forms. I mean, just look at the matter around us. The kind of forms, many ways they present themselves, all coming from the same rules. And electrons and nuclei, nothing more. They're amazing. And then lasers, for example, all part of this quantum world, and eventually the same laws leads to life and us. And here we are contemplating all these laws. It's quite an amazing phenomenon. Alright, so what are these? So I have to tell you a little bit about quantum mechanics. So I'm sure many of you have been exposed to it, but since it's a public lecture, I thought I should tell you a little bit about it in as simple a way, using as little mathematics as possible. So what are quantum waves? You're familiar with waves. When you talk about waves, they are waves of typically particles, or sound vibrations will be waves of pressure or something. So the question is, what is waving in quantum mechanics? Why do you talk about quantum waves? So these are actually, unfortunately, they are not waves of anything that we are familiar with. They are waves of complex numbers representing probability amplitudes for possibilities which are changing with position and time. And so there is something called a wave function, which is the sum of some real part and the square root of -1 times another real number, and it's written as this. This is as you know, this is called a complex number. And the probability of finding a particle, for example, an electron at position x and at time t, is the modulus squared of this complex number, and that's the sum of a squared plus b squared. And there's no way to avoid using these two different parts of this complex number. And you may say, hey, after all, what is measured is only this probability density. Why do I need this probability amplitude? I can just deal with this. The point is, if I have an experiment with several alternative possibilities, like for example, an electron can go on one path and another path, and I don't determine which path it takes, then to find the probability of the electron reaching the final place, I have to add these amplitudes for the two possibilities and then square it. And that leads to interference, and that leads to all the fantastic possibilities of wave phenomena, such as interference, standing waves, wave packets, etc. And that's the point about having to work with this probability amplitude. And then, as a result, in quantum mechanics, I can only make probabilistic predictions for experiments in general. And one central aspect is, what are the types of wave functions that occur in different contexts? How do they evolve with time? Alright. So for example, here is an example of a wave function. Like I am actually plotting the modulus square, the probability density. For a free particle, it can be put into this kind of a state, which is a wave packet. And you can see the probability density is large in some region of space and very little elsewhere. So you can, this is the closest quantum mechanics comes to describing what we think of as a particle, which is like a lump of energy. This is localized here, and then as a function of time, it moves pretty much the same way as classical particles move. And that's the reason, in fact, classical mechanics works, because the quantum mechanics has this underlying feature. But one thing it does is, as it moves, it also spreads. Okay. Now, if you go to, I'm sorry. Oh, that's the wrong one. What is the? Yeah, so if you go to electrons and atoms, then the waves that are important are what are called standing waves. So here is an example of different types of standing waves and the probability density associated with that. And you can see it has these interesting structures. They are called like cell structure. So this is one particular standing wave, this is another standing wave, this is a third kind of standing wave. Just like, like ripples you can imagine in a pond. This and ripples in a pond. Okay. And the important point is that each of these standing waves, each standing wave is corresponding to a fixed energy of the electron, just like if you were to take a drum and hit it, you get standing waves. And each standing wave of the drum corresponds to a particular frequency of vibration of the drum. It's the same kind of math, same kind of phenomenon there, except that the frequency here corresponds to the energy of the electron. And they are related by this thing called constant called the Planck's constant. And then, so this is the lowest energy standing wave, and there are more standing waves at higher energy and more and more. And you can see that different energies are kind of separated by discrete amounts. So we call these quantized energy levels of an electron in an atom. Okay. And the other important point is that when the electron interacts with the electromagnetic field, it can cause a transition from one level to another level, and then emit or absorb a photon, which is like a quantum of the electromagnetic field, so that the change in energy of the electron transfers to the energy of the photon or vice versa, where this h is the Planck's constant and this nu is the frequency of the light. So it's an amazing connection. Frequency of light is something that you normally associate with wave, right? And yet this lump of energy is a property of the quantum, which is a photon, which is particle-like. Again, photons have dual nature, particle and wave. Energy, momentum, everything. Okay. So because of this, you get actually only some particular photons of particular frequency, and therefore if you do spectra of atoms, you'll get sharp lines in absorption and emission spectra. Now when you go to multi-electron atoms, the picture is very similar. Actually, these will get slightly modified and the energy scales will become larger, but still you have many of these standing waves, and you have many electrons now, and all the different electrons populate the different standing waves, and which can be up or down. And if you have two, like an up electron and a down electron can populate the same standing wave, but if I have two up electrons, they cannot be in the same standing wave. So you will take all the electrons in the atom, which in higher nuclei atom, higher atomic number atoms, there have been many electrons. You will put, for example, you can put in helium atom, you can put two electrons in this, one with upspin and another downspin, and so on. And in the next one, you can put one more electron here, and then more electrons here, etc. And then it turns out that if all the energy levels in a particular region of energy are occupied, you get what are called closed shells. Those are like helium atom and so-called rare gas atoms, and they are completely happy and they don't interact chemically at all. But if you have one electron or small number of electrons floating around and many of these levels are empty at the same energy, then you get other atoms which interact with each other, and that's the basis of chemistry. So as an example, in carbon, which has 6 electrons, 2 of the electrons occupy the 1s, that's kind of happy, but the other 4 electrons can now, they have interesting angular structure, those standing waves. So they can, for example, form such standing waves, and there are 4 electrons occupying these. But they would like to partner with one more, because each of these standing waves would like 2 electrons ideally. So if a neighboring carbon atom comes, then the 2 together will chemically bond, and sort of this lobe will sort of mix with the lobe of the next carbon atom, and they'll form a bond. Okay. Similarly, you can have another arrangement of the same kind of standing waves, which is called sp2 hybridization, and then they form graphite. This is diamond, this is graphite. So just the properties of the standing waves and how they are oriented in space determining how atoms bond together to form molecules and solids, etc. Okay. So if you apply quantum, so basically we can understand pretty much all of solids and their properties starting from this principles of quantum mechanics and putting atoms together and how they electron. But without quantum, even though the motion of center of mass motion of atoms and molecules, except inside solids at low temperatures and in cold atom traps related to this topic that I come to, they are nearly well approximated by classical mechanics. So the electron motion has to be treated by quantum laws, and that's crucial for the distinction between metals, insulators, semiconductors, the working of diodes, transistors, integrated circuits, computers, superconductivity, quantum dots, wires, the electronics of the nano world. I mean, so this whole subject is known as quantum matter. Okay, and in particular, using this quantum matter, people are working furiously on computers of the future called quantum computers. If I have time, I will come and tell you a little more about it towards the end of the talk. Alright, so conventional solid-state materials, which are metals, semiconductors, old superconductors, they are describable in terms of these electrons moving around in standing waves, which are now propagating throughout the crystal. Okay, so I can kind of ignore the interaction between the electrons and think of them as each electron as separately, except for this Pauli principle. And then there are, just like we had photons, which are quanta of electromagnetic field, there are quanta of lattice vibrations called phonons, and there is a very good theory of solids in terms of these entities, which is well understood, well known, and that is the foundation of all the, they were all developed in the 20s and the 30s of the last century, and then that was the crucial importance for understanding semiconductors and responsible for all the technology that we enjoy today. But there are many materials, so let me skip the details of this, I don't have time. But there are many new materials that have been discovered in the last 20-30 years. One example is this thing called superconductor, called two-plate superconductors, which were discovered in 1986 and fetched a Nobel Prize for its discoverers. Until about 1986, the highest critical temperature of superconductivity was about 20 Kelvin. That means that is, like at minus 250 degrees centigrade, right? So if you didn't cool materials to that lower temperature, you would not get superconductivity. But suddenly, starting from their work, we had superconductors well above liquid nitrogen temperature, about 120 Kelvin. But today, the theory for these materials doesn't exist. Okay. And why is that? Because these are what have come to be known as strongly correlated electron systems. That means the electron-electron interaction effect in these materials are very strong, and I cannot use the well-known theories of superconductivity and solid-state physics of the last century to understand these materials. So we are still struggling. So that's one of the frontier areas of theoretical research, and for example, I'm also engaged in that. But and this is where one of the motivations for the ultra-cold atom that I'm going to tell you about comes in. And this is sort of the structure of this material. Let me skip the details of this. But the point is that Richard Feynman, who I'm sure all of you have heard of, is a famous physicist, Nobel laureate, and written this fantastic series of books called Feynman Lectures on Physics, which is like a very inspirational reading for any person who wants to do that. So he talked about a possibility of a quantum analog simulator where one design a quantum system which you build emulating a different physical system. So one of the motivations for people to study this ultra-cold trapped atoms is that, as I will tell you, that's what I'm trying to convey in this talk, is that this system of ultra-cold trapped atoms in optical lattices, which can be engineered, or actually very good analog simulators of strongly correlated quantum materials. So you can say, how does that help? The way it helps is roughly as follows. Here is this very complicated two-plate material. Okay. When we try to understand the properties of that, we physics people, we often make a simple model of it. For example, it turns out that the most important ingredient in these two-plate superconductors is a plane consisting of copper and oxygen atoms. Okay. So if you focus on that thing, it turns out that you can ignore all the electrons in the system except for one lone electron in each side. If I have time at the end, or if somebody is interested, I can tell you how it comes about such a simplification. But just one electron in each unit cell of this lattice hopping around from side to side, and if there are two electrons sitting on the same side, it costs an extra repulsion energy because they have the same charge. Right? So we can make a model which is as simple as that, and many people believe that that model actually should be able to explain the properties of this. But we don't know how to solve this problem because the interaction is large. Right? And you make various approximation schemes and try to compare with experimental data about the phase diagram of the system and various details of the system, and it doesn't agree. Then you don't know, is the approximation bad or is the modeling itself too simple? You have no idea. Right? But that's where a quantum simulator can come in. And you create this experimental system of cold atoms which mimics this model, and you study it experimentally and then see whether it has properties similar to two-plate superconductors. If it does, then you know that this model is okay, because this model exactly represents this cold atom system. Then you can worry about approximation scheme and test it against measurements, and this is a much more controlled system where you can tune all the parameters of the system, unlike smarter systems. So that's the idea, that's the role. Okay, so that's kind of the background why we are interested in these ultra-cold atoms, or at least one of the reasons. Okay. So before I tell you, I have to tell you about cooling and trapping of neutral atoms. How do you cool them? And the coldness I'm talking about here is nano-Kelvin. It's the coldest place in the universe. These systems that people, there's no other place in the universe that we know of which is as cold as the scientists have made these systems. Okay, so it has a long history, and these two gentlemen got a Nobel Prize for developing the techniques for cooling. Okay, so I have to first tell you about the cooling of how do you cool. It's actually very clever. Okay, so the cooling is done using laser beams. You might say, hey, that looks very surprising, because normally, if you think of a laser, you associate it with heat, right? You hit something with laser and you can use laser to cut metals and stuff like that, right? So how can a laser be used to cool atoms? So it uses this I told you, for example, when an atom makes a transition from one level to another, it emits a photon. Right? Now, a photon carries energy and momentum. Now, because of energy and moment conservation, the atom has to experience a recoil, just like when you fire a bullet from like a moving vehicle which is on rails, right? The bullet is fired and then there's a recoil of the gun or... So exactly the atom experiences the recoil. So the idea is, if you have an atom which is going in that direction and you put a laser beam and then one photon is absorbed by this atom, then that absorption of the photon will give a kick to the atom in this direction. So the atom will slow down. Right? So that's the basic idea. And you remember, cooling is connected with slowing them down because according to kinetic theory of gases, basically if you have atoms, then the kinetic energy of each atom at temperature T is proportional to the temperature. So if you can reduce the kinetic energy of all the atoms, that will be equivalent to cooling the atoms. Okay. But you can say, hey, after the after the atom absorbs the energy, it will re-emit it in the form of another photon, but that will go in some random direction, and therefore it will experience another kick again. But the point is, the difference is that all the atoms move in this direction. When they absorb this photon, their velocity will slow down, but this random velocity will kind of average to zero. So, but you can say, hey, what happens if you have the atom moving in the other direction to start with? And that absorbs the photon, it will get a kick in the same direction it was moving, so it will speed up. So this is not going to work. But what these people do is something very clever, which is they use something called the Doppler effect, which I'm sure all of you are familiar with. It's the same effect that when if you are near a train, right, and the train is moving past you, when it's coming towards you, the frequency of the sound that you hear is shriller and it goes away, it decreases. Actually, so the same effect is used in engineering this. Let me tell you about that a little bit. So because actually when an atom absorbs a photon, like I told you in a very simplified picture, that corresponds to a short energy level. But it's not exactly short. Actually there is a profile like this, right? That the absorption is maximum at a central frequency, which corresponds to the short level, but there is some deviation on either side. So there will be some slightly less absorption on this side and that side. Okay. So the idea is that if you imagine that you tune the frequency of the laser light so that it's somewhere there, rather than at the center here, right? So then an atom moving towards the laser light will see a Doppler shifted frequency which is higher, which will come up to here and absorb with maximum probability, whereas an atom that is moving away will be shifted further this side and will be absorbing with less probability. So by using the Doppler shift in this clever way, you can engineer it so that the atoms coming towards the laser beam will absorb and slow down, and the atoms moving away from the laser beam will not absorb with the same probability. Yeah? I hope that's clear. So you can in fact show that actually, so if you look at the rate of absorption of momentum, the rate of absorption of light by the atoms is the rate of absorption of momentum. It's like a rate of change in momentum, is like a force. So it's like a force. So the force depends on the velocity with which the atoms are moving, and you have atom moving this way have a force profile like this, and the atom moving like this have a force profile like this. If you put it together, you will find that there is an effective net force which is proportional to the velocity and like this yellow curve here, and acts exactly like friction. So it kind of slows all the atoms down. So that's the basic phenomenon of laser cooling of atoms. And in fact, because the random emission in all directions, there is no net velocity, but the atoms still have some kinetic energy. So you find that you cannot cool this, use this technique to absolute zero. There is a lowest limit of temperature, which is determined by the width of that resonance curve I showed you, and that's about like 10 microkelvins. So this was actually the technique invented by these people for which they got the Nobel Prize. And next question you can ask is, okay, I've succeeded in cooling, but they still have some temperature, whether it's microkelvin or whatever, and therefore atoms are still going around in random directions. So if you don't contain them in some way, they fly apart. So then people trap them using something called magneto-optical trap. And the way that is done is like you have an arrangement of coils like this, and then you create a magnetic field which is changing with distance from the central point. And then if there are atoms here, they will be moving in different directions. And what you can do is you take atoms which have these, the ground state has some level, only one level, and the excited state has 3 levels with different quantum numbers. And you can arrange it so that there's a laser which is tuned to a frequency such that when the atoms comes here, it will absorb, and the atom coming here will absorb, but the atom coming there will absorb that light, and then they'll get a kick towards the center. So basically, you arrange it so that the laser light is being absorbed by just the correct type of atoms, so that they get kicked back towards the center. So it's called a magneto-optical trap. So in fact, in one of my colleagues, Professor Vasan Natarajan, has built this kind of apparatus, and then you can see, I don't know if you can notice here, this is this cloud of atoms here, of interbeam atoms. So people can trap about 1 million atoms like this, cooled down to microkelvin by this technique alone. Okay. If you want to cool further, then you use something called evaporative cooling, which is analog of how you cool a hot cup of tea. By blowing on it, then you remove all the atoms or molecules with very high energy, so that the remaining thing has less energy and therefore colder. So you can do something which is analog of that by using magnetic trap and radio frequency fields. I'm going to run out of time, so let me skip the details of that. I'll be happy to explain it to you, anybody interested. So, alright. So, let me tell you a little bit about this thing called the Bose-Einstein condensation. So the first physics idea that these cold atom systems were used to test was an idea associated with our own Satyendra Bose, who proposed a new way of deriving Planck's law from the principal statistical mechanics. And Einstein he sent his paper to Einstein, and Einstein took that idea further and saying that in addition to light, it can be also applied to types of particles called bosons. And he showed there's something called Bose-Einstein condensation that will result, which is where at low enough temperatures, all the particles of bosons, unlike electrons which are called fermions, they cannot occupy the same quantum state or the same standing wave. Bosons like to occupy the same standing wave. So at 0 temperature, for example, Einstein showed, in fact, below a critical temperature, a large fraction of the bosons will condense into the same standing wave, and then as a result, you'll get something called a Bose-Einstein condensate. But this idea had not been tested because it requires cooling materials to very low temperatures, and so let me skip the math and show you kind of in terms of picture. So the idea is that if you have high temperature, you can picture a gas of atom more like billiard ball. They are atoms moving around, colliding with each other, and running around, etc. But each atom is really a wave packet, like I explained earlier. So there is a wavelength associated with it, which depends on the velocity of the atom and therefore on the temperature. So this picture, a classical picture applied at high temperature, where this wavelength of these wave packets is actually very small compared to the interparticle separation. But if you keep cooling, eventually these waves will start overlapping, and then the quantum mechanics will kick in a big way, and you will get a post-condensation where all the waves, all the particles actually condense into one particular quantum state, one particular wave. So it's like this is, for example, the lowest standing ray in a box, and all the particles will be, all the bosons will be in this thing. It's called a giant matter wave. So that's the idea of Bose-Einstein condensation. And so the root was, actually there is a real Bose-Einstein condensate in nature called helium-2. It becomes a superfluid around 4 Kelvin. But the point is, but that has a very high density of particles, so the helium atoms are too close together, and then the interaction effects are too strong. So it's not the kind of Bose-Einstein condensate that Einstein considered, where a non-interacting boson. So whereas if you take this dilute gas of atoms which are very far apart from each other, but then you require a much cooler temperature, like 10 to the minus 9 Kelvin. And when these people did this experiment, they showed that actually it was cool. Okay, so you can say, how do you tell whether there is such a thing as Bose-Einstein condensate? So one of the imaginative experiments that we will do in these cold atom systems is something called time of flight measurements. It turns out, so if you take this cold atom with a trap and suddenly remove the trap, which you can do by turning off the magnetic field and the lasers, right? Then they fall under gravity, and then so they fly in different directions. So how far apart this cloud spreads is a measure of what the initial velocity distribution was when it was inside the trap. And you can image that, and therefore you can actually find out how many particles had what kind of momenta in the initial state. And that's called time of flight technique. And here's this famous experiment which won these people a Nobel Prize, which is that you'll find that high temperature, you'll find that velocity, this is actually a picture of the momentum distribution of the particles. You'll find that the particles have a wide momentum distribution, right? And as you cool down, you'll find that a large number of particles are kind of piling up at essentially zero momentum, which corresponds to Bose-Einstein condensate. And there was this theoretical curve, and then these are the experimental data, and it actually fit absolutely on top of the theory. So this was the first verification of Bose-Einstein condensate, and for which they obtained Nobel Prize. Okay, so this is again another illustration of the fact that the difference between Fermi particles and Bose particles. So if you take different atoms, like a different amount of neutrons in the nucleus, if you take what's called the isotope of lithium called 7 lithium, and that's a boson. If you take something which is 6 lithium, that is a fermion. Okay. And here you can see the Bose condensation forming, or atom piling up at the center, but here in the case of Fermi particles, they don't pile up, so there's a big difference between them. So these are all things. Okay. Now that, in addition to having these experimental verifying dilute limit, non-interacting things, you can also induce interaction between these atoms inside these traps using something called the Feshbach resonance. Let me skip that. By having this atom in a magnetic field and tuning the magnetic field, it turns out that you can control the interaction between one atom and another atom. So using that, you can actually do lots of experiments of interacting atoms inside a trap. For example, there is some theory of one-dimensional gas of interacting particles, because you can arrange to confine these in one dimension, and again, there is a lot of theory, and you can make experiments. So let me running out of time. Let me skip the details of this and tell you about optical atoms. So there is a new era in ultra cold atoms which are using something called the optical atoms. I'm sure all of you are familiar with interference. Like when I have two laser beams, for example, they interfere and produce standing waves. So if I have two laser beams going this direction and two laser beams going that direction, I will get a standing wave like this. If I have 6 laser beams going in all 3 directions, I can get a standing wave pattern of this. So where these dots represent the maximum or the minimum of the electric field. Okay. So the electric field is maximum here, minimum in between, maximum here, and minimum in between. The square of the electric field. And it turns out that if you were to put atoms in the presence of such a field, they'll experience an effective potential which is proportional to the intensity pattern in this interference pattern. Okay, so that means the atoms will be attracted to that place and that place and that place wherever these balls are. So this is exactly like electrons in a crystal. So electrons in a crystal experience a periodic potential. They are attracted to the centers of where the nuclei are. Okay. So this is completely mimicking that. So it's kind of an artificial crystal made up of atoms, which one is creating using laser beams. And when you have that, so you can track each atom in these wells. Okay, and then an atom can tunnel from one well to the next well to the next well. And if two atoms come to the same well, they'll have a strong repulsion interaction or an attractive interaction depending on how you tune the magnetic field I told you about. So you can create systems where you have electrons that can tunnel quantum mechanically from one well to another and have experience an interaction when they are on the same well. So that's very much like the simple model I was telling you about of superconductivity, where I said if there's an electron on one side, two electrons on one side, they try to repel, and the electron move from one unit cell to another. So in fact, this exactly mimics, depending on whether these atoms are fermions or bosons, they mimic the simple model that I told you about called the Hubbard model. So which is difficult to solve, and therefore the idea is that you could study this system and try to understand the properties of the Hubbard model. Okay. So this is the basic idea of this thing called the optical lattice emulator. So it will hopefully resolve long-standing questions in condensed matter by laboratory simulation. And there are also experiments that you can do in these optical lattice systems which you can never do in the laboratory in condensed matter systems, which is all kinds of non-equilibrium experiment, because the parameters of that model that I told you about, like the amplitude with which an electron moves from side to side or the interaction, they can all be tuned. So I can suddenly change the system. It's a system in equilibrium and some value of the parameter, and I suddenly change the values of the parameter and see how the state of the system evolves. There are all kinds of non-equilibrium experiments of this sort that you can do in these systems which are not possible. So that's the extraordinary interest in these systems. So for example, there's something called the Bose-Hubbard model, which is the analog of, so the idea is that you have these wells, this is the periodic potential created by this optical lattice, and you put Bose particles in each well. Okay. Now, if the interaction is very strong, and for example, if you have on an average one particle per well, okay, if the interaction is very strong, then the particles like to keep apart, because I don't like to have two particles in the same well, right? Or for example, if I have two particles per unit cell, then it would like to arrange itself in this way: two particles here, two particles here, two particles here, two particles here, two particles here. Then this will become something called an insulator. It mimics an insulator in normal materials, because if a particle has to move from one end of the sample to another, it has to encounter this repulsion energy and it will not move. Okay. However, if the interaction is weak, the particle would like to move from side to side, and they form this thing called, which I was telling you about, called the Bose condensate. Okay. So you'll find that if the interaction is weak, you'll get what is called a superfluid, and if the interaction is very strong and the number of particles per unit cell is an integer, you'll get this thing called a Mott insulator. Okay. So the experiment that, for example, was done by Greiner et al., which in fact showed this exactly. That they found, for example, that if the interaction is very strong, then if you look at this momentum distribution of the particles, if the particles are localized in space, that the momentum distribution of that particle is uniform. Whereas if the particles are mobile and Bose condense, you'll find this everything condenses at this Q equal to 0 point, or it's kind of periodically repeated because of the periodic potential. So this was in fact the first demonstration that actually this model has this transition which theory people had predicted. So similarly, there are all kinds of other predictions of theory that people have verified. For example, if you have this trap potential, there is an overall trap potential in this problem which I didn't mention. So I showed you these regions of Mott insulator. It turns out that if you have a trap potential which is changing with position, at the central region where the trap potential is minimum, you would like to have more particles. So you get regions with 3 particles per cell, regions with 2 particles per cell, and regions with 1 particle per cell, arranged in something called a wedding cake structure, like this. And that people have predicted like this. And in between regions are superfluid, and people actually have verified that it works like that. And there are lots of other things that people are able to do now. You can actually do imaging of these atoms in these optical lattices, and you can do single side image. You can tell whether an atom is present in one cell or not present in another cell. That's like a two-state system. If you have on an average less than 1 atom per cell, you can say whether a particular site is occupied by an atom or not occupied by an atom. And then these atoms can move around. So this two-state quantum system, like where a particle is present or not present, is something called, which is the quantum analog of what you know as a bit in computer. In computer bits, you have 0 or 1, right? 2 states. Like here, an atom can be present, which is 1, let's say, or 0, which is a different quantum state. But remember, in quantum mechanics, I can superpose 2. So there's a possibility that it's present and not present. That's something that is peculiar to quantum mechanics, and that means, and if you have many such sites, like many qubits, simultaneously it represents all possible choices for zeros and ones at each of them. You know that, like in binary mathematics, right? If I have a string of digits which are zeros or 1, a string of zeros and ones represents an integer. Right? On the computer, if I have memory, that depending on the registers, which of them are zeros and which of them ones, it represents one integer. So, and I have to operate with these integers. A quantum collection of quantum bits simultaneously can represent all possible, like suppose I have n quantum bits, n qubits. It can simultaneously represent all integers that you can make with n strings of zeros and ones. And then you can do computing with this. And so these are the computers of the future. So these cold atom systems are one possible candidate for building such computers. So that's another reason for the extraordinary interest in this. So I think how am I doing for time? I should stop. Okay. So let me show you, for example, some of the kind of experiment that people can do. Like people can put these fermionic particles in optical lattices, and you can do the analog of squeezing. You know, like you take an ordinary gas, right, and you compress it and expand it in normal experiment that you do with gases, right, by using a piston. But here you have some optical trap potential, and you can tune your magnetic field and electric field, etc., to squeeze the thing or expand the thing, and then find out how the atoms respond. So that's kind of a non-equilibrium experiment. Okay, so this is another very interesting aspect of cold atoms. So I don't know how many of you heard of something called QCD. Like, for example, nuclei are made up of protons and neutrons, and we know now that protons and neutrons are made up of other smaller particles called quarks, and quarks interact with each other with some entities called gluons. And there are gluons and quarks come in 3 colors, people say. Okay, it's a way of distinguishing different types of quarks and different types of gluons, and the interaction between quarks and gluons is analogous to the interaction between electrons and electromagnetic field, but more complicated, because the maths is much more complicated, and it's called non-abelian. It's a technical term connected with what is the symmetry of these quantum fields that represent these gluons and so on. Okay, it turns out that there is a way of arranging systems of cold atoms such that the interaction between atoms in this cold atom system mimics the interaction between quarks and gluons inside the nuclei. Okay, so this is a way. Okay, so I think it gets a little bit too technical for me to tell you. If anybody is interested, I will be happy to share that with you. But that's another exciting development, which is that this same system, so this is called a synthetic magnetic field or synthetic non-abelian gauge fields. Basically, by manipulating the interaction of these atoms with light and using, in fact, Raman spectroscopy and so on, it turns out that you can create effective interaction between these atoms, which are analogous to interaction between atoms and magnetic fields. Because normally these atoms are neutral, right? So they will not interact with the magnetic field. Only charges interact with magnetic field. But here you can create, by these techniques, interaction of electron with, neutral atom with magnetic field, and you can also create this non-abelian gauge field, etc. So that's another exciting field. And then I mentioned this thing about the squeezing. This is a non-equilibrium experiment. There is another experiment that people do in these optical lattice, something called, which is lattice modulation or Bragg spectroscopy. Which is, I told you that the atoms are trapped in this periodic potential, and you can tune the strength of that periodic potential. For example, you can pull down the periodic potential and then increase it and decrease it, right? And then what the effect of that is that this well becomes deeper and shallower, and that very strongly affects the rate at which the atoms tunnel from one well to another. That's a very sensitive function of the depth of this potential. So it's like taking one of these models that we have and making the hopping of an electron from one cell to another a function of time. You can never do it in a condensed matter system, but here you can do it, and then you can ask what are the consequences of that. So that's of great interest in non-equilibrium statistical mechanics, so we will study such issues. There are other things that you can do. You can kind of load atoms into the optical lattice with a fixed predetermined pattern. You can, for example, do something analogous to I'm sure all of you have like a swing. You're familiar with a swing, right? Or a pendulum. You give it a kick and it oscillates back and forth. And eventually it die down because of friction or viscosity. Here, for example, you can take this system of cold atoms and give it an impulse and then watch this whole cloud of atoms oscillate back and forth, and eventually that motion will die down because of the internal viscosity of the atoms. And you can use these experiments to determine that viscosity and then compare against theoretical calculations of that. So it's a fantastic experimental tool for understanding theories of strongly correlated quantum matter. So there's a lot of scope for the future. And also I mentioned about quantum computing. Not only can you trap cold atoms, but you can also similarly take ions and cool them. And cold ions is another very hot subject like this, and which can again have a very important application in quantum computing. So these are some very exciting developments awaiting us in the future. So I think that's all.
Good evening, ladies and gentlemen. Sir has explained beautifully the fascinating world of utter code and that order. It has been very informative and exciting talk, sir. On behalf of Bangalore Science Europe and all of us here, I propose to welcome to Dr. H.R. Tomorrow's talk by Dr. S.N. Omkar, Chief Research Scientist, Department of Aerospace Engineering, Indian Airforce, will be speaking on uninhabited aerial vehicles for all the inhabitants. Our party will invite. Any questions, please?
Super. This is the first question I asked. The name of it, your name of the position.
Myself, Mehta, National Guard. Are you using the same technique in trapping and cooling the particle of heterogeneous gas molecules, or only that?
No, say again.
Can we use the same trapping technique what you right now we are using? Can you use the same technique in trapping the particle of heterogeneous gas molecules, like different gas molecules at a time?
No, these primarily work with atoms, because once you go to molecules, so atoms have a slightly simpler, this is crucially dependent on being able to absorb a photon from a particular frequency, which is very well separated from other energy levels, and a particular pair of energy levels is involved, and you have to fine-tune the laser frequency and detuning the Doppler effect, etc. Molecules, what happens is they have too many energy levels, because when you make a molecule, it can rotate, it can vibrate, etc. And all those energy levels come in and mess up the energy level structure. It's much more complex. So what happens is this whole experiment becomes much harder for molecules than for atoms. So we use.
Is it possible in future there's like?
I don't know, because the scientists are very clever, so maybe they will it from there.
Anyone else?
So what is the applications of superconductivity? Where all they apply superconductivity?
Okay, I'm sorry, I didn't talk much about superconductivity. So the point is, superconductivity is basically a material which has zero resistance to electrical current flow. And you can imagine what a boon that would be, because, for example, all the electrical current power that is supplied to us comes via generator, comes via cables, and because of resistance of the cables, there's enormous loss, right? So if you were to have superconducting cables transmitting power from the generator to our homes, there will be no loss, basically. So that will be one application. Unfortunately, because of this problem that for a long time, the superconducting materials had to be cooled to 22 Kelvin in order for them to be superconducting. It's not practical because how do you cool cables running across 1,000 miles to that lower temperature? It's not practical. So ideal would be if you had a room temperature superconductor, then which you didn't require to cool, then that would be the fantastic material and there would be no power loss. So that's one application. And so research goes on. Hopefully somewhere in the future somebody will find a room temperature superconductor.
Okay.
But so the other application, which is very important application, if people know about, is something called magnetic levitation.
Yes.
Which is if you take a superconductor and try to put it in front near a magnetic field, you'll find that the magnetic field is expelled by the superconductor and therefore it's repelled by the magnetic field. So if you had a superconductor and took it near a magnetic field, it would experience repulsive force. So you can imagine either having the, if you had like a room temperature superconductor, you could either make the rails with superconducting material or the train with superconducting material and the other with a magnet, and then it would float. Right? So there would be no friction. So you could have trains traveling at incredible speeds. In fact, you can do it with magnets alone. Of course, you know that if you have opposite poles, they repel. So in fact, right now, there are experimental trains in China and many other places where they just use magnetic levitation, using this repulsion of oppositely polarized magnets to create these trains. But superconducting trains would be much better. But,
The introduction of atom warfare threatens the very existence of the civilian throughout the world.
no, I'm sorry, I couldn't make out.
These general questions.
Can you say it? I didn't.
So you know when we come in train,
You may not actually need a mic.
and 1 minute is allowed, no? You can finish it.
There is a question.
No, why is not necessary?
No, I can ask a question. I couldn't make out what you asked.
The introduction of nuclear warfare, it creates the very existence of civilians throughout the world.
Yes.
And especially civilian Russian.
Okay.
Civilian Russian. They create the branch of third world war.
Nuclear energy you're talking about.
Third world war.
I'm sorry, I can tell you privately my opinion about it, but not sorry connected with the topic.
Yes, I told you about the quarks and other particles, subatomic particles in the nucleus. So how do you explain the near forces or strong forces inside the nucleus?
Yeah, so that's actually connected with this thing that I was telling you about. The quarks, because of the nature of the gluons and the quarks, this thing I told you that 3 types of quarks and 3 types of gluons. It turns out that the effective interaction between quarks and one quark and another, you know that if you have like a repulsive interaction or an attractive interaction between unlike charges, right? It dies with distance, right? As 1 over r square, like Coulomb's law between charges is like 1 over r square. But if you take effective interaction between quark and quark, you will find that the interaction becomes very strongly divergent as you separate them. It goes linearly with distance. So basically different types of quarks with different charges would like to stay as close together as possible. And that's why actually quarks are never seen by themselves. They bind together, form protons or neutrons. Like the triplet of quarks forms a proton or a neutron. And then, so the interaction between one neutron and another neutron, or one neutron and another proton, which you normally think of as a nuclear force, is actually connected with this internal force between quarks. But because the quark-gluon thing is completely satisfied, there is no force if you separate like this triplet. There is no force. The force comes only when they touch each other, basically, practically.
No, whatever, see, you like.
So myself, Somshekar, first year BSc student. So when you are telling you are trapping an atom in a potential well or using a magnetic field, don't you think you are violating Heisenberg uncertainty principle there?
Pardon?
When you are trapping an atom in a magnetic field or a potential well, the Heisenberg uncertainty principle.
No. Because the thing is, what Heisenberg uncertainty principle says is that you cannot simultaneously measure the position and momentum of a particle to arbitrary accuracy. Okay. So the point is that it doesn't prevent you from trapping. First of all, electrons are trapped inside atoms, right? Like an atom wouldn't exist if the electrons are not trapped inside the atom. So it doesn't violate things. It's just that what it requires is that the fact that it's confined in a small region means that it has a kinetic energy. It has momentum uncertainty, which is determined by Heisenberg uncertainty principle. It means it has some kinetic energy. The smaller you want to trap it, the higher the kinetic energy. But then in order to trap it, you're also using potential energy. So then it's grenade. So there's no fun.
Please come, sir. This would be the last question. Please.
No, one exact question. Do you still agree with the theory of Dr. John Sudarshan, who discovered icons? Is it still relevant even today?
About tachyons.
Tachyons, right?
I don't know. Because the point is, see, in physics, the criterion for relevance or non-relevance is experiment. In all science, actually, right? The proof is experiment. Right now, there are no experiments that demonstrate the existence of tachyons. So it's not. But nobody is saying that it's impossible. Right? At least, serious scientists. But it's something for the future. Maybe some future technology will allow you to experimentally probe such things. But if you look at all these science fiction movies like Star Trek and other things, you find that they routinely talk about tachyons and other particles, etc., saying that technology has been invented in the far of the future. Maybe it's true or not. But at the moment, we don't know a way of exceeding the velocity of light. But what is true is that, so the issue is, ordinary particles like the matter particles that we're familiar with cannot, according to special relativity, they cannot exceed the speed of light. Similarly, tachyons can never come below the speed of light. They are on the other side. But whether they can ever talk to each other or interact with each other, whether they can do experiments, is something in the future.
Thank you, Professor Krishna Murthy. I am closing the session. If you have some questions, when you go, you can ask.